Hello, this video is for Stat 310 Handout number 11, Part B, and will cover pages 10 through 16. Okay, let's go ahead and get started. Part B will again use the Find Cars, Used Cars dataset that is available in our Google folder for Handout 11. So Part B is going to consider an unequal slopes model. In Part A, the model that we fit forced the slopes to be the same. Here we're going to allow a model in which the slopes can differ. So this is a continuation of the Find Cars dataset. We subsetted out the data to only include the Toyota vehicles. You can see Part A for that. The model that we fit in Part A looked like this here. Had a beta 0, beta 1 times miles, plus a beta 2 times model. And that model there was an indicator variable, either a 1 or a 0. So model number 2 here is going to be a less restrictive model, and it allows for the slopes to differ. The only difference between model number 1 and model 2 is this additional term here. So that last term on the end. Now that last term is called an interaction term, and that term is going to allow for the models to be allow for the slopes to be different than one another. The form of model here is an indicator again, which just has a 1 or a 0 setting. The interaction term is either going to be miles, so this should be miles here, sorry about that, it's a typo, copy and paste. The indicator term here is going to be 1 times miles for a Camry, and it's going to be 0 times miles for a Corolla vehicle. Okay, so when I do the multiplication with an indicator, I'm either going to end up with miles or I'm going to end up with 0. Because again, that indicator variable is just a 1 or a 0. How do I fit this model in JUMP then? Well, there's two things that have to be done here in addition to what we've done before. The first is to get that interaction term in the model. And you can see that down here. We do that with the cross. So I'm going to need to use the cross button there under Construct Model Effects. The other thing that we often will do is underneath this model specification dropdown, I can select or uncheck centered polynomials. So we'll talk about both sets of output. When this box or when this centered polynomials is checked, you'll get a certain set of output, or when it's not checked, you'll get a different type of output. So I'll talk through that as well. So let's just quickly go over into JUMP here and fit this data. I'm using the data again just on the Toyota. I have it color or marked by the colors as we had from Part A. I'm going to select Analyze, Fit Model. Mile or price is going to be what I'm interested in predicting. I'm going to use miles. I'm going to use make model. So this is model 1 here. I need to add that interaction term, which I am selecting the model, holding down the control button, and selecting miles. And now I use the cross here to get that interaction term. And the other thing that you can do is either deselect or select the centered polynomials. By default, centered polynomials is selected. If I take it off, okay, I'm going to take it off here for at least part of this output. It's a little bit easier to understand the output with it off. And then I go ahead and click Run. And now from my regression output, you can see here that I have slopes that are not parallel to one another. At least for the data that I have, they don't seem parallel to one another. They get closer together as the miles increase. Excuse me. The summary of fit, analysis of variance, and parameter estimate output is again down here on the bottom. We will talk through all of that output next. So let's first talk about what happens when I check or uncheck the centered polynomials. So if your output looks like this on the right here, then centered polynomials has been specified. And I know that because it's not using miles right here, but it's using miles minus 66,584. Now that 66,584 is just the average miles for everything in the data set. For all the values in the data set, all the miles, what's the average? It's right at $66,500. So when JMP did the fit, it actually used this instead of miles. If you take off the centered polynomials, then it just uses miles. Now, let's look at the output. A lot of this output is the same. The y-intercept, 17,983, 17,983. It's actually the same for both of those. Actually, the test and the p-value are the same for the intercept. The miles, minus 0.08, that's the slope here. That's the slope that I have over here when centered polynomials is checked. So there's actually no difference in miles. There's no difference actually in the output for the last term here. This is the interaction term. You can see that I'm taking the indicator variable and multiplying it by miles. That output is actually the same on both sides. 16.03, 16.03 is the p-value for both of those. The only thing that's different here is the indicator variable. On the left I have 1,374, but over here I get about 932. What's happening when I uncheck the centered polynomials is that this beta 2 hat term is again the change at the y-intercept. So how much of a difference do I have over here at the y-intercept? About 1,300. On the centered polynomials, that change is for when the miles are at 66,584. So it's actually not testing at the y-intercept, but it's instead testing right in the middle of my data. So that jump between the two, in the middle of my data, the jump between the Corolla and the Camry is 932 in the middle, and it's about 1,375 over here on the edge. Certainly those values are different, those standard errors are different, so I'm going to get different p-values between those two tests because they're testing at different spots. When the lines were parallel to one another, I didn't need to worry about where I was testing because the gap between both lines was the same irregardless of the miles. But that's not the case when I'm fitting a model with unequal slopes. So there's not really a right or a wrong to which output to use. You just need to understand what that test is providing. I'm going to go forth with the output on the left. Here I have an R squared of 87.9. Now before, when I had the equal slopes model, my R squared was 87.5. So this more complicated model that allows for the slopes to be different isn't really helping me too much. It's helping me a little, but not much. Likewise, the R square or the root mean square error here is 1,437. With the equal slopes model, that root mean square error was 1,449. So again, not much of an improvement. If I want to write out the models, I would use the intercept and the miles for a Corolla again, because remember, for a Camry, the indicator term is equal to 0 when I'm talking about a Corolla. That's how JMP has set it up. I know that because Corolla is missing here. So this intercept and miles is for the Corolla. So I can just pull off the 17,983 and the minus 0.08, and that's going to be the equation of the blue line. So if we go back up here and look, the equation of the blue line is given by 17,983 minus 8 cents a mile. The equation for the Camry, or the red line, is going to have these additional terms in here. This is the beta 2. The 13,074 gets attached to the y-intercept. Okay. This interaction term of negative 0.01, this has miles on it, So that's going to get attached to miles. So the miles, the effect or the slope for the Camrys is going to be the 0.08 that I had initially, but then I'm going to subtract another 0.01 here. And that's where I'm getting 0.09. So that slope for the Camry is a little bit steeper than the slope for the Corolla. And you can see that in the regression lines. The red line is a little bit steeper than the blue line. The interpretation of this 0.01 is just the additional decrease in the price per mile due to being a Camry. Okay, so let me say that one more time. The beta 4 hat in this model is just the additional decrease in price per mile because I am a Camry. The 1374 value is the additional, that would be an increase in the price of a new Camry. So when the miles is 0, I can expect a Camry to be about $1,300 more than a Corolla. So that's the interpretation of those two quantities. Interpretation of the intercept and the miles is just the slope and the y-intercept for the Corolla. We've already talked, well, test number 1 and test number 2 are the same as what I had in part A. So they're just testing again. This first one is just for the Corolla. It's obviously going to be different than 0, so that's going to be significant. The miles, okay, now that's for both vehicles, both types, because beta 1 appears in both of these models. So beta 1 appears in both of these. So that is testing the slope for both. P-value number 3 again is just saying that I do indeed have a difference at the y-intercepts. The estimate is positive, which tells me that the Camry is costing more than a Corolla. It's less than 0.05, so it's significant. Test number 4 is also, test number 4 is not significant. It is not less than 0.05. So that's saying that I cannot say that the slopes are different from one another. Now you can see that this estimate, 0.01, is pretty close to 0 here. I mean, granted, it gets multiplied by a pretty large value, but the effect of the miles, or the extra effect on miles due to being a Camry, is pretty small, especially considering to what it was initially. So I'm not really changing the slope too much. So I cannot say that the slopes are different from one another. Now again, you might say, well, from the lines they look different from one another. Yeah, but that's only one snapshot of what could be happening. If I go get another set of data, the blue dots are going to change, the red dots are going to change, the lines are going to change. And those two slopes are too close to one another to say that they're different. Again, what determines that is p-value number 4 here in that list. So the effective miles, okay, the depreciation on miles between these two types of vehicles is not really that different. This third one, though, is significant. So that is saying I do have a price difference between a Camry and a Corolla. It just, that price difference doesn't change as a function of miles. We can also obtain the 95% confidence intervals. Let me just show you where that's done, because that's kind of hidden up here. I would go under regression reports and say show all confidence intervals. And that will give you the 95% confidence intervals for each of those parameter estimates. Here's some final comments. Test number 3 suggests that there is a difference in the expected price between a Corolla and a Camry. And that expected price is about $1,374. And that's actually at the y-intercept. I should probably add that in there. The 95% confidence interval for that parameter right here is about $670 up to about $2,000. That confidence interval does not catch 0, so I know I have a difference here. Test number 4 seems to suggest that the effect of miles on price is similar for those both types of vehicles. This confidence interval here does capture 0. The upper endpoint slides a little bit above 0 there. So 0 is a likely value for that parameter, so I cannot say that there's a difference between those. The p-value here is 0.16. So I would advocate using model number 1 over model number 2 for the following reasons. Well, the main reason is I don't really need the two separate slopes. Test number 4 said I did not need two slopes. So there's no reason to use this more complicated model. Model number 2 is more complicated and it has that interaction term in it. If that's not significant, if that's saying I don't really need two separate slopes, then don't use model number 2. And that would advocate using model number 1. From model number 1, again in Part A, we learned that there was indeed a difference between a Corolla and a Camry, and that model allowed for that. It was that constant, or that parallel lines, so that increase was the same irregardless of miles, but there was a difference between those two types of vehicles. We should check the assumptions from model number 1, and I provided the residual plots down below for that. If you want to make predictions, then you can go ahead and use model number 1 for those predictions. All you're going to need to know is the miles of the vehicle, and then indicate whether or not it's a Corolla or a Camry. And when you're making those predictions, you would plug in 0 for the model for a Corolla, and 1 for the model for a Camry. So let's quickly look at the residuals down here. This is the residual plot from model number 1 now. Model number 1 had a root mean square error, I think, of about 1,450 or so. Multiply that by 2. I'm right at 2,900. So anything that would be above 2,900 or below 2,900 would be an outlier. I do have a couple of outliers down here on the bottom. How about the others, though? Linearity. That looks okay. I don't have any unusual patterns here in this plot. I do have a gap here, but we're not concerned about the gap. I want random scatter above and below this line, and I have that. I have that for the red line dots, and I have that for the blue dots. So this model seems to be working for both models of vehicles, both the Camry and the Corolla. Constant variance, yep, that looks okay. I don't have any megaphone. I don't have any strong autocorrelation, positive or negative, so that's good. Normality is down below. We'll show that here in a minute. And the outliers here, I went ahead and saved the I saved the residuals, so I can do that from my drop-down menu. I can just say Save Columns Residuals here. We did that in handout number 10, I think. And then I just found the residuals that were very, very negative here. You can just sort that data based on the residuals, and you can easily find those. So those are those two observations there. Both of these vehicles are fairly low in price, and they don't have a whole lot of miles. But the reason their price is dampened is because they're somewhat old. These vehicles are over 10 years old here. So my model, actually, the actual price is much lower than what I would have predicted based on this number of miles. Again, the reason that they're outliers is because they're so old. I haven't taken into consideration the year of the vehicle here. I'm just looking at the miles. Handout number 12 would allow me to look at more than one predictor variable. Here's the residuals. Again, just make a histogram of those. The histogram looks a little bit skewed to the left. Doesn't look real nice and normal there, but the normal quantile plot doesn't look bad. We're still within these bands, so I feel pretty comfortable with the normality assumption. So model number 1, after looking at the residuals, seems like it's a good model. I have a fairly decent R-squared and root mean square error, and again, you can use that model to make predictions. Okay, that does it then for Part B of Handout 11. Thank you.